Now let's look at some more examples computing expected value. So in our last video, we looked at an example in which we flipped a fair coin 3 times. And in that one, we looked at X being the number of heads we saw. Let's consider the same experiment. So flip a fair coin 3 times. But I want to define a different random variable. So here, I'm going to let Y equal the number of heads multiplied by the number of tails. And in this case, let's now once again try to compute the expected value of this random variable. So recall that our sample space consists of the 8 outcomes we listed before. And now we need to think about, again, the range of my random variable. So range of Y. And if we think about the different extremes that could happen here, we could have that the number of heads is 0 and the number of tails is 3. Or the number of heads is 3 and the number of tails is 0. Both of those lead to the possibility of the product being 0. The other considerations are that you have 2 heads and 1 tails, or 1 heads and 2 tails, and in both cases the product would be 2. So there's really only 2 possible values that Y takes on. Next, we have to find the mass density function. So the mass density function of this random variable will then again require that we compute P of 0 and P of 2. So the probability that that this random variable is 0 would include the probability that you see all heads or all tails. So that's really 2 out of 8 outcomes. The other 6 outcomes deal with having 1 head and 2 tails, or 2 heads and 1 tail. And all of those lead to a product of 2. And again, I check and I see that my mass density function sums to 1. And finally, I'm at a point where I can now compute the expected value of Y. Again, we take 0 times P of 0 plus 2 times P of 2. That first part cancels out, so we really are taking 2 times probability 3/4, and we end up with our expected value of 3/2. Another example, different context, is suppose instead now that you play a game where you roll 2 fair 6-sided dice. If the sum of the rolls is greater than 9, you win $2. Otherwise, you lose C dollars. Find the value of C so that this is what we call a fair game. So given our terminology here, when we talk about a fair game, then we're thinking of your expected winnings being 0. So not positive, not negative, but 0. So we want to figure out how to ensure that the expected value is 0. What we can do is at least find what the expected value is as a function of C, and then come back and use that. So again, expected value, we've got this random variable. I want to consider the range of my random variable. So there are only 2 possibilities. I guess maybe before I do this, to be completely clear, when I'm referring to X, whoops, too far. I'm kind of assuming that's my random variable, so let's define that. So let's let X be your winnings. So that's the random variable of interest. And in particular, it's the expected value of that I want to be equal to 0 in order to have a fair game. Now, when I refer to x now, I'm a little bit more clear on what that is. So the range of x being my winnings, we see there are two possibilities after playing this game once. I can either win $2 or lose C dollars. In order to reflect a loss, I'm going to put in a minus sign for C. So then for the mass density function, I need to be able to find the probability of each of these things. So the probability that I win $2 and the probability that I lose C dollars. So to find this, I would come back and recognize if the sum of the rolls is greater than 9, then we want to consider that the sum is equal to 10, 11, or 12. Now you could look back at an earlier video where we actually computed the probability that the sum of two die rolls adds to different values. But in particular, to see a sum of 10, there were 3 ways that could happen. So we could get 6, 4, 5, 5, or 4, 6. To get a sum of 11, it had to be 5, 6, or 6, 5. So 2 ways. And then there was only the possibility of 6, 6 to get a sum of 12. So all told, we see that we get 6 out of 36, or 1/6 chance of winning $2. If anything else happens, we lose C dollars. So I'm really using the complement rule here to say that this gives me 5/6. Then I would be able to say that my expected value is then 2 times P of 2 plus minus C times P of C. So in this context, 2 times 1/6 minus C times 5/6. So fair game, like I said before, implies that we want the expected value of our random variable to be 0. So in this context, that means we want 0 to equal 2, 6 minus 5C over 6. 0 should then equal 2 minus 5C. 5C should equal 2, or C should equal, 2/5. So again, recall that C is the amount we should lose in the instance that we don't see a sum greater than 9, and we're saying that we should lose 2/5 dollars. So I would want to include my units there, and we get this. So again, this is depending on the definition of the expected value, but in this instance, we knew what we wanted the expected value to equal, and we needed to make that happen by finding the value of C. So one last example, and I'll point out this is going to connect why we're covering probability in our Calc 2 course. So suppose that you keep flipping a pair of coins until you see the outcome HH, so both come up heads. Let's define the random variable x here to be the number of times you need to toss the pair for this to occur. So given that definition, so the experiment and our random variable, again, we can consider some different things. What is the range of x? So we want to think about the possible values that x can take on. So in order for this to occur, seeing the outcome heads, certainly we'd have to at least flip the pair once. So the smallest possible value of x is 1. It could take us 2 times, it could take us 3 times, 4 times, and so on. And in fact, there's no upper bound on the number of times that this could take. So this is the first example we've seen in which the range here is infinite. So there are infinitely many values. of random variable x. So that's a new situation for us. So in this instance, if we were asked to find the mass density function, we have to take a different approach. So far, finding the mass density function required us to list the value of the function p evaluated at everything in the range of x. Now there are infinitely many things in the range of x. I can no longer list all of the mass density function values there. Instead, the goal is to try to come up with some kind of pattern so we can come up with a general representation for, say, p of k. To do that, think of the first several. So p of 1, again, in the context, that's saying what's the probability that it takes one toss of 2 coins to see heads. Thinking that there are 4 possible outcomes on that toss, the probability that they land heads is 1/4. P of 2 is now asking us to consider the probability that it takes us 2 flips of the fair coins for this to occur. And this means 2 things. This means that on the first flip of those coins, we did not see heads, otherwise we wouldn't have made it to the second one. So the probability that that didn't occur on the first toss of those is 3/4. And on the second, the probability that we did see that is 1/4. You might note that I'm multiplying here for and. So because we're assuming we have fair coins, and in fact, the fair coin has nothing to do with it. What I'm assuming is that the outcome of my first flip of the pair of coins has no bearing whatsoever on the outcome of the second flip. And so that's a reasonable assumption to make. So we're assuming that those tosses are independent. So P of 3, again, is saying that on the first 2 occurrences of flipping these coins, we did not see heads, and then on the third, we did. Notice that I can express that as 3/4 squared times 1/4. And if I'm starting to try to look for a pattern, I can see that the one above was 3/4 to the first power times 1/4. And this was 3/4 even to the 0th power times 1/4. And in general, following that pattern or just thinking about the context, if I'm looking for P of k, that's saying that on the first k minus 1 flips of this pair of coins, on all of those, I did not see heads. So I represent that with a 3/4 raised to the k minus 1 power. And then finally, on the kth occurrence, I do see heads, and that's representative of a 1/4. So this here, again, would represent us finding the mass density function in the instance where I have infinitely many values in the range of my random variable. So thinking about it this way here, there's a couple things to consider. Let's see. So if we know that the mass density function, if you're to sum over all possible values of the random variable, which in this case we said would be whole numbers 1 to infinity, equals 1. This is from the probability principles, if you will. So what's interesting about this is that this now introduces an infinite sum of positive numbers, right, of the form 3/4 to the k minus 1 times 1/4, in which I know that that infinite sum has to equal a finite value. And not only does it equal a finite value, a relatively small finite value. So we have infinitely many values being added together such that the total sum is 1. So what we want to think about is that that's just due to the context, but in particular, that means that this sum from 1 to infinity must be 1. And this leads to the question, how would we know this without the context of probability? So that's what we're going to lead into now in the next several lectures is the discussion of infinite sums. And it's a very complex topic. Part of the reason we start with probability is we get a situation where we can see that it's believable that I can add infinitely many values and get a finite number. But also we're going to be able to point back to some of these concepts once we develop some understanding of infinite sums. And we're going to be able to compute these mathematically to in fact prove that we would get 1 with that, which would match our intuition here from how we're defining probability principles. So from this point on, we're going to move on to a big Calc 2 topic series, and we're going to devote several lectures to talking about that. And you'll see that throughout, when possible, we'll link it back to probability.